Every world in the solar system has its own survival clock. On some, the danger is vacuum. On others, it is heat, pressure, radiation, or cold so deep that survival becomes a question of engineering, not endurance. In this video, we explore how long a human could survive on each planet and what those worlds reveal about how rare Earth really is. If you enjoy calm space documentaries, please like the video and subscribe to the channel. Far from the Sun. The solar system opens into a region where survival is defined first by absence. There is no breathable air, no stable surface warmth, and no protective blanket of atmospheric pressure. The outer solar system is not one single place, but a broad domain beyond the giant planets, where sunlight grows weak and cold becomes the default condition. In this setting, the primary hazards are not dramatic storms or ground-level dangers. The primary hazards are vacuum, radiation, and temperature, acting steadily and without pause. Vacuum means near zero pressure. Human lungs and blood are adapted to life under an atmosphere that presses inward with consistent force. When that force is removed, the body begins to fail quickly. Breathing becomes impossible because there is no air to inhale. Oxygen in the bloodstream begins to fall. Consciousness can fade within a short span as the brain is deprived of oxygen. At the same time, water in exposed tissues begins to boil at body temperature, not because it becomes hot, but because the surrounding pressure is too low to keep it liquid. This process can cause swelling and damage, though it is not an instant explosion. The body remains held together by skin and tissue, but it is not designed to function in such conditions. Survival without protection in vacuum is measured in minutes at most, and useful activity is measured in far less. Cold in the outer solar system is not simply the cold of winter air. It is the cold of deep space, where sunlight is weak and the background temperature of the cosmos is only a few degrees above absolute zero. Yet cooling in vacuum is slower than many expect because there is no air to carry heat away by convection. Heat leaves mainly by radiation, the slow emission of infrared energy. Even so, over time the body loses heat and becomes hypothermic if it is not protected and warmed. In the outer solar system, where sunlight provides little external warmth, any unprotected object tends toward extreme cold. The skin and outer tissues cool first, then deeper tissues follow. Temperature is therefore a long pressure, not a sudden strike, but it becomes inevitable without shelter and energy input. At the same time, sunlight is not the only radiation hazard. Space is filled with energetic particles. Some come from the sun as solar wind, a stream of charged particles that flows outward through the solar system. Far from the sun, this wind becomes thinner, but it still carries energy and can intensify during solar storms. Other particles come from outside the solar system as cosmic rays, fast-moving atomic nuclei accelerated by distant astrophysical events. These particles can penetrate deeply into materials and living tissue, damaging cells and electronics. On Earth, much of this radiation is reduced by the atmosphere and by the planet's magnetic field. In deep space, those shields are absent. Radiation becomes a steady background that accumulates over time. It does not usually kill in minutes, but it can injure quickly in intense events and can increase long-term risk during prolonged exposure. There is also the hazard of impacts. Even in the emptiest regions, tiny grains of dust travel at high speed. Small particles can strike a suit or spacecraft and gradually erode surfaces. Larger micrometeoroids are rarer, but they exist. The danger is not constant like vacuum, but it is part of the environment. A human in a suit relies on the suit's integrity. A puncture that allows pressure to escape can become fatal quickly if it cannot be sealed. In the outer solar system, distance from immediate rescue makes such failures more consequential, not because physics changes, but because time and isolation increase the importance of reliability. Survival time therefore depends on what kind of protection exists. With no protection at all, vacuum dominates and survival is short. With a functioning pressure suit, the problem changes from an immediate suffocation and pressure loss to longer-term resource limits. A suit supplies breathing gas, removes carbon dioxide, controls humidity, and regulates temperature. It also provides some shielding from radiation and micrometeoroids, though not complete. In the outer solar system, a suit must provide more heating than it would near Earth because sunlight is weak and the environment is cold. It must also manage heat generated by the body and by suit electronics, radiating excess energy away without freezing critical systems. These are engineering constraints, not mysteries. They determine whether a person can survive for hours rather than minutes. A habitat changes the situation further. A pressurized shelter can maintain Earth-like pressure, breathable air, and stable temperature. It can store water and food, recycle some resources, and provide stronger shielding. Yet a habitat in the outer solar system must be built and powered. In deep cold and faint sunlight, power often relies on nuclear systems or other long-lived sources rather than solar panels alone. Heat must be generated and retained. Materials must endure long thermal cycling, radiation exposure, and mechanical stress. A habitat must also protect against the slow leakage of air, the contamination of water systems, and the accumulation of harmful chemicals. None of these challenges is impossible in principle, but each requires careful design and maintenance. The outer solar system adds another quiet constraint: time delay. Signals travel at the speed of light, far from Earth. Communication delays increase, and real-time guidance becomes less practical. A human presence would depend on local autonomy and robust systems. If a failure occurs, there may be no quick external intervention. This amplifies the basic physical hazards because it reduces the margin for error. Survival becomes not only a matter of moment-to-moment protection, but also a matter of long-term system stability. In this outer setting, the concept of surviving on each planet begins with a shared baseline. Every world beyond Earth lacks the surface conditions that humans require without technology. The key requirement is pressure. Without pressure, breathing stops and the body begins to fail quickly. The key secondary requirements are temperature control and radiation shielding. Without them, longer survival becomes difficult even if pressure is maintained. On Earth, these conditions are provided naturally. In deep space, they must be built. The outer solar system is also a place where the body's limits are clear and the environment's calm is deceptive. A view of dark space and distant starlight looks peaceful, but physics remains strict. In vacuum, the body cannot exchange gases with the surroundings, cannot protect its internal fluids, and cannot maintain normal function. In cold, it loses heat by radiation over time. In radiation, it accumulates damage invisibly, particle by particle. In this way, the outer solar system is not hostile by intention. It is simply indifferent, governed by pressure, energy flow, and particle environments that do not adapt to biology. This baseline also sets a useful comparison for the worlds ahead. Some planets have atmospheres, but those atmospheres are unbreathable, too thin, too thick, too hot, or too cold. Some have strong magnetic environments that increase radiation exposure. Some have surfaces, and some do not offer any solid surface at all in the ordinary sense. Yet beneath these differences, the underlying survival problem remains consistent. Humans survive when pressure, Oxygen, temperature, water, and radiation levels remain within tolerable ranges. When these conditions are absent, technology must replace them, and the time a person can endure depends on the strength and duration of that replacement. In the far outer solar system, where the sun is dim and the background dominates, survival without protection remains brief and limited. With protection, survival becomes possible but still constrained by power, materials, and the need to keep a small Earth-like environment intact against vacuum and cold. This calm outer baseline becomes the first region of the journey, a quiet statement of what space demands before any planet is even approached. Beyond Neptune, the solar system becomes a colder, darker place where sunlight weakens into a distant glow. This region is often described as the Kuiper Belt, a broad band of icy bodies and remnants left from early solar system formation. The Kuiper Belt is not a neat ring of evenly spaced objects. It is a scattered population spread across a wide range of orbits, with some bodies moving in resonances shaped by Neptune's gravity. The space between them is enormous, and most of the volume is empty. The environment is defined less by what it contains than by what it lacks: dense air, strong warmth, and local protection from energetic particles. In this region, survival begins with the same first requirement as anywhere in open space. Pressure is absent. There is no breathable atmosphere, and there is no surrounding force to keep body fluids stable. If a human is exposed directly to this environment without a sealed suit or habitat, the outcome is rapid and consistent. Breathing stops immediately because there is no air. Oxygen in the blood falls, and consciousness fades quickly. Swelling begins as pressure drops and gases expand in tissues. Water in exposed areas begins to boil at body temperature because the surrounding pressure is too low to keep it liquid. These effects unfold quickly and do not depend on distance from the sun. Vacuum behaves the same everywhere. The Kuiper Belt therefore does not create a new kind of unprotected survival. It extends the same vacuum limit into colder, darker conditions where rescue and support are less plausible. Cold becomes more influential here because sunlight provides very little heating. Sunlight still exists, but it arrives weakened by distance. The energy that falls on surfaces is far lower than near Earth. This affects not only comfort but basic thermal balance. In vacuum, the body loses heat mainly through radiation rather than through moving air. This can mislead intuition. A person does not freeze instantly because there is no wind to pull heat away. Yet over time, without active heating, temperature falls. In the Kuiper Belt, external warming from sunlight is minimal, so anything that radiates heat tends to cool toward a very low equilibrium. The human body generates heat internally, but that heat must be conserved or replaced. A pressure suit in this region must function more like an insulated life support system than like a simple barrier. It must retain heat, provide controlled warming, and prevent critical parts from cooling below operating limits. A suit must also manage the opposite problem under certain conditions. Heat can build up inside sealed systems even in cold space. Electronics, pumps, and the body itself produce heat. In vacuum, removing heat requires radiators and careful control of internal airflow. A suit in the Kuiper Belt therefore needs both insulation and the ability to shed excess heat when activity is high. The environment is cold, but thermal control remains an engineering balance rather than a one-directional slide into freezing. The Kuiper Belt also raises the importance of power. Near Earth, sunlight can support solar panels effectively. Far beyond Neptune, sunlight is too weak to provide high power with practical panel sizes, especially for life support and heating. Long-duration survival in this region relies on stored energy and long-lived generators. Nuclear systems, whether radioisotope heat sources or reactors, are often the most practical options in concept because they provide steady output independent of sunlight. Batteries alone are limited. Any habitat must run pumps, fans, heaters, and carbon dioxide removal systems continuously. A failure of power becomes a failure of pressure and temperature control. In deep cold and vacuum, a power loss can turn a habitat from safe to lethal through a chain of predictable steps. Air circulation stops, heating stops, carbon dioxide builds, humidity control fails, and internal temperatures begin to drift. Radiation adds a quieter pressure. The Kuiper belt lies outside Earth's magnetic shield and outside the protection of a thick atmosphere. The solar wind still streams outward, though it becomes more diffuse with distance. In addition, cosmic rays remain present, arriving from far beyond the solar system. A short exposure to space can be dominated by the immediate threat of vacuum. Over longer periods, radiation becomes a major constraint for health and for equipment. Radiation can damage living tissue by breaking chemical bonds and causing mutations. It can also degrade electronics, causing errors and cumulative failure. Shielding helps, but shielding adds mass. In the Kuiper belt, where supply and resupply are difficult, long-term survival becomes linked to how well a habitat can provide thick, reliable shielding using local materials. Local materials exist in abundance, but mostly as ice and rock. Many Kuiper belt objects are mixtures of water ice, frozen gases, and rocky components. Some have surfaces rich in complex carbon compounds that are dark and absorb what little sunlight arrives. These bodies are cold enough that many volatile substances can remain frozen on or near the surface. This provides opportunities for resource use in a theoretical sense. Ice can be melted into water and split into hydrogen and oxygen. Rock can provide structural material and radiation shielding. Yet accessing these resources requires energy for excavation, heating, and processing. In the Kuiper belt, energy is the key currency. The environment offers matter, but it does not offer easy power. Gravity on most Kuiper belt objects is weak. Small bodies have low mass, so surface gravity can be far below Earth's. This matters because weak gravity affects how dust and gases behave near the surface. A habitat built on or within such a body would not benefit from strong gravitational settling of air and dust. It would also face challenges for human health if a person remains long-term in very low gravity. Observations indicate that prolonged low gravity affects muscles, bones, circulation, and balance systems. Artificial gravity can be created by rotation, but this adds design complexity. For survival measured in hours, low gravity is not the dominant hazard. For survival measured in months or years, it becomes part of the long-term burden. The Kuiper belt environment is also quiet in one way that matters for hazards. The density of small, fast-moving particles is low compared with regions closer to the Sun where dust from comets and asteroids is more common. Yet the risk is not zero. Micrometeoroids exist throughout the solar system. Over long periods, even rare impacts become likely. In a sealed habitat, a small puncture can cause gradual pressure loss. A robust design uses multiple layers, internal compartments, and monitoring systems that detect leaks early. In deep space, redundancy is not a luxury. It is the main method for extending survival time from hours to months. Light and darkness shape psychology and physiology as well, though they do not change the physics of survival. In the Kuiper belt, the sun appears as a bright star rather than a warming disk. Daylight on a Kuiper belt surface is dim and cold. Shadows are deep. A human habitat would likely rely on internal lighting to maintain stable day-night rhythms. Without such structure, sleep cycles can drift. this is not an immediate lethal hazard, but it becomes part of long-duration living. A stable environment must support the mind as well as the lungs and skin, because poor sleep and chronic stress reduce decision quality and weaken resilience during emergencies. In this outer region, the question of survival time becomes a matter of definitions. Unprotected exposure remains brief because vacuum dominates. With a properly functioning suit, survival can extend for hours, limited by oxygen supply, carbon dioxide removal capacity, water, battery life, and thermal control. With a robust habitat and reliable power, survival can extend far longer in principle, because pressure, oxygen, and temperature can be maintained. The limiting factors then become durability, radiation dose accumulation, maintenance capacity, spare parts, and the ability to keep a closed life support system stable. The Kuiper belt therefore serves as a calm extreme in the solar system. It is not a place of violent weather or rapid change. It is a place of steady constraints near vacuum, deep cold, weak sunlight, and persistent radiation. Survival. There is not about outrunning storms. It is about holding a small pocket of Earth-like conditions against an indifferent environment for as long as engineering and power allow. This outer region sets a baseline for the worlds inward of it, where atmospheres, magnetic fields, and stronger sunlight add their own complexities while never removing the basic need for pressure and protection. Neptune's domain begins long before any imagined descent into its blue atmosphere. Around the planet lies a wide region shaped by gravity, sunlight that is already faint, and a strong magnetic environment generated deep within the planet. Neptune is an ice giant. It does not offer a solid surface that can be stood upon in the ordinary sense. Its visible boundary is a thick atmosphere that grows denser with depth, passing from thin upper layers into pressures and temperatures that become steadily more extreme. In this region, survival is not mainly a question of finding a safe patch of ground. It is a question of whether any protective system can maintain pressure, temperature, and shielding while the surrounding environment becomes more hostile the deeper one goes. In open space near Neptune, the first survival limits remain those of vacuum. Any unprotected exposure still ends quickly because there is no air and no pressure. With a sealed suit or shelter, the story depends on resources and reliability. The sun is far away, so sunlight provides little heat and little power. A suit must conserve heat, and a habitat must generate it. Solar panels, if used, produce far less electricity than they do near Earth, because the same light is spread across a much larger area by distance. Long-duration survival near Neptune therefore depends more naturally on stored energy and long-lived sources such as nuclear power. This is true even before Neptune's atmosphere is considered. In this outer region, survival is shaped by steady cold and the need for continuous life support operation. Neptune's magnetosphere adds another layer. A magnetosphere is the region of space influenced by a planet's magnetic field, where charged particles are guided and trapped. Neptune's magnetic field is unusual in its geometry. It is tilted relative to the planet's rotation axis, and offset from the planet's center. This creates a magnetosphere that changes with Neptune's rotation in complex ways. Charged particles from the solar wind interact with this field, and some become trapped, forming radiation belts. The intensity of Neptune's radiation environment is generally less extreme than Jupiter's, but it is still a consideration for long-duration exposure. Charged particles can damage electronics and contribute to radiation dose for living organisms. Shielding reduces the risk, but shielding adds mass and complexity to any mission. Neptune's gravity is significant, though less than Jupiter's. Gravity matters for two reasons. It influences trajectories, making close approaches demand careful navigation. It also shapes what happens during atmospheric entry. When a craft begins to descend, it does not drift gently into a calm sky. It accelerates and it compresses the atmosphere in front of it, producing heat. Entry heating is one of the first major hazards of reaching deeper layers. A protective heat shield can manage this, but it must be designed for the speed, angle, and atmospheric properties of Neptune. The atmosphere is made mostly of hydrogen and helium, with methane contributing to its blue color and to its chemistry. These gases are not breathable. They contain no oxygen for human lungs and would be lethal if inhaled even at tolerable pressure. In Neptune's upper atmosphere, pressure can be low enough that a suit must still supply full pressurization. The temperature is extremely cold. The planet receives little solar energy, and its cloud tops lie in a deep chill. Yet Neptune also emits internal heat, energy left from formation and from slow gravitational contraction. This internal heat influences the atmosphere and drives weather patterns. Neptune's winds are among the fastest measured in the solar system, reaching speeds of thousands of kilometers per hour in some regions. Wind is not directly relevant to survival in a sealed suit in the way it is on Earth, because there is no breathable air and no exposed skin. Yet wind becomes relevant for any craft or platform trying to remain stable. Dynamic pressure, the force of moving gas, increases with both wind speed and atmospheric density. A balloon, probe, or suspended habitat would need to handle strong shear, turbulence, and changing conditions. Stability becomes difficult, and failure can mean loss of control and descent into deeper, more lethal layers. As descent continues, pressure rises steadily. This is one of the defining features of gas and ice giants. There is no thin boundary where a safe surface begins. There is only a gradient, with air becoming thicker and heavier. For an unprotected human, the change is lethal long before pressure becomes extremely high, because the gas is unbreathable and the temperature is far outside the range that a body can tolerate. For a protected human inside a sealed craft, the danger comes from the increasing external pressure. A habitat must maintain a stable internal pressure. The structure must resist the growing force pushing inward. On Earth, pressure outside and inside a body are nearly balanced. In deep planetary atmospheres, external pressure can rise to many times Earth's surface pressure. A rigid structure can resist for a time, but as pressure increases, the required strength rises quickly. At some point, the materials and design limits are exceeded, and crushing failure occurs. Temperature also rises with depth. In the upper atmosphere, cold dominates. Deeper down, compression and internal heat lead to warmer conditions. Eventually, temperatures become high enough to destroy ordinary materials and overwhelm cooling systems. The combination of high pressure and high temperature is especially destructive. Even if a craft could resist pressure, heat would stress seals, weaken structural components, and degrade electronics. Cooling in a dense atmosphere is different from cooling in space, but deep inside Neptune, the ambient heat is not something a small system can easily reject. The environment becomes the hotter reservoir, and a craft can no longer radiate heat away effectively. It must endure heat rather than remove it. Neptune also contains chemical and physical transitions at depth that remain uncertain in detail. Observations indicate an interior rich in water, ammonia, and methane in forms that behave differently under pressure than they do on Earth. These substances may exist as hot, dense fluids, and deeper still, they may enter exotic states. For survival questions, these details matter less than the broader physical trend. Depth leads to rising pressure and rising temperature. The deeper a descent continues, the less plausible it becomes for any human supporting structure to remain intact. Survival time at Neptune therefore depends strongly on location and protection. In open space near Neptune, with a functioning suit or spacecraft, survival can extend as long as life support and power remain stable, which can be hours, days, or longer in principle. Unprotected survival remains brief, limited by vacuum, as it is anywhere. In the atmosphere, unprotected survival is effectively negligible because the gas cannot be breathed and pressure is not suitable. With protection, a craft might remain in the upper atmosphere for a limited time if it can control altitude and handle winds, but the hazards are severe. Without active control, descent continues, and deeper layers become rapidly fatal for any human presence. The practical survival window inside Neptune's atmosphere therefore collapses quickly, unless the system is both strong and precisely managed. Neptune's environment also makes rescue and repair unusually difficult. The distance from Earth implies long communication delays and long transit times for any support mission. Even if a failure is detected, immediate help is not available. This makes reliability central. A safe human presence near Neptune would depend on multiple layers of redundancy, careful shielding, stable power, and a robust thermal system. It would also depend on staying out of the atmosphere's deeper regions, treating the planet as an object to observe from above rather than a place to inhabit within. In calm scientific terms, Neptune represents an outer boundary where the solar system's planets shift from solid worlds to deep atmospheres with no accessible surface. Survival there is not about adapting the body to the planet. It is about maintaining a sealed pocket of Earth-like conditions in a place that offers none. Near Neptune, vacuum and cold define the baseline. Within Neptune, pressure and heat rise without a stopping point. The planet's beauty remains real, but its hospitality does not exist for biology. Survival is therefore a matter of engineering held against gradients that become steadily more extreme as the blue world draws closer and deeper. Section 4. Uranus sits inward of Neptune yet remains part of the cold outer realm where sunlight is weak and life support systems cannot depend on warmth from the sun. Uranus is also an ice giant, with no solid surface that can be reached and stood upon. Like Neptune, it is defined by an atmosphere that thickens with depth, with pressures rising continuously until any familiar notion of surface becomes meaningless. The calm appearance of Uranus through a telescope, a pale disk with subtle banding, hides an environment shaped by low temperatures, unbreathable gases, and pressure gradients that become lethal as soon as descent begins. In the space around Uranus, survival again begins with the vacuum baseline. Without protection, life ends quickly because breathing stops and the body cannot function without pressure. With a sealed suit or spacecraft, survival depends on stored resources and the reliability of life support. Sunlight at Uranus is still too weak to provide abundant power with practical solar collectors, so long-term operation favors internal power sources, especially for heating and systems control. In this region, a human can survive as long as air, pressure, temperature control, water, and carbon dioxide removal continue to operate. The environment outside remains quiet but unforgiving. Radiation near Uranus is influenced by its magnetosphere, which is unusual in geometry. The planet's magnetic field is tilted relative to its rotation axis and is offset from the center. This creates a magnetosphere that changes in structure as the planet rotates, producing complex interactions with the solar wind. Uranus does not have radiation belts as intense as Jupiter's, but charged particles can still be trapped and guided, and the radiation environment remains relevant for long-duration missions. radiation damage accumulates over time and can degrade electronics and increase health risk. Shielding and mission planning reduce exposure, but they cannot remove it entirely. Uranus is also distinctive in its axial tilt. The planet's rotation axis lies almost on its side compared with the plane of its orbit. This creates extreme seasons that last for long portions of its long year, with one pole facing the sun for extended periods and then facing away. This fact is striking, yet it does not make the planet warmer in any human sense. The sunlight is weak, and the atmospheric temperatures remain extremely low. The unusual seasons mainly influence atmospheric circulation and the distribution of light across the planet, rather than creating any zone that is naturally comfortable for life. A descent into Uranus's atmosphere brings immediate biological impossibility without protection. The atmosphere is made mostly of hydrogen and helium, with methane contributing to its color and chemistry. There is no oxygen to breathe, and the gases themselves do not support human respiration. At the upper levels, pressure is still too low for survival without a pressurized suit. Temperature is far below the freezing point of water. A person exposed directly would lose consciousness quickly because of lack of oxygen and pressure, and the cold would deepen injury. The fundamental barrier remains pressure and breathable air, long before the deeper hazards appear. For a protected human, the key issue becomes the external environment's steady change with depth. Atmospheric pressure rises as altitude decreases. The structural challenge of resisting pressure grows with it. A craft designed to float at a certain pressure level might avoid the deepest compression for a time, but it must remain stable against winds, turbulence, and vertical motion. If it drifts downward into denser layers, the force on its hull rises, and the temperature begins to climb as well. The atmosphere does not offer a single stable platform. It is a three-dimensional moving fluid with long-term circulation and local variability. Uranus is often described as less internally active than Neptune in terms of visible storm activity, yet this does not mean it is safe. The planet's low apparent heat output compared with Neptune suggests a different internal energy balance. Observations indicate that Uranus emits less internal heat relative to what it receives from the Sun than Neptune does. The reasons remain an area of study, possibly involving differences in interior structure or heat transport. For survival, the exact cause is less important than the overall reality. The upper atmosphere remains extremely cold. Deeper layers become warmer and higher pressure. The absence of strong visible storms does not provide a habitable zone. It provides only a calmer-looking cloud deck. As depth increases, pressure reaches levels that crush ordinary structures. Engineering can resist pressure up to certain limits, but the requirements grow quickly. A habitat designed for Earth-like pressure inside must keep its internal pressure stable, while resisting the much larger pressure outside if it descends too far. At high external pressure, even small structural flaws can propagate into catastrophic collapse. In addition, temperature increases with depth. Materials weaken, seals fail, and electronics degrade. The deeper the descent, the more the environment behaves like an industrial furnace under compression, rather than an atmosphere that can be navigated safely. The question of how long a human could survive on Uranus therefore has a careful answer. On the planet itself, meaning within its atmosphere, unprotected survival is effectively none. There is no breathable air and no stable pressure. Protected survival is limited by the ability to remain in a narrow band of the upper atmosphere, which is difficult because there is no surface and no simple anchor point. A craft could, in principle, hover or float at a chosen pressure level using buoyancy or propulsion, but it must handle winds and maintain energy and thermal control. Even if it succeeds, Survival time is then determined not by the planet's generosity, but by the craft's life support and resilience. Without active station keeping, descent continues and becomes fatal by crushing pressure and rising heat. In the space around Uranus, survival is limited by the same factors that govern deep space pressure containment, oxygen supply, carbon dioxide removal, water, food, and thermal control. A person in a spacecraft with sufficient supplies could survive for days or longer. Yet the outer solar system's distance makes resupply difficult, and long missions require robust recycling and radiation management. The planet itself adds no natural support. Its role is to increase complexity and risk if descent is attempted. Uranus is also surrounded by moons and rings. These are not central to the planet's atmospheric hazard, but they matter to the broader idea of survival in the Uranian system. The moons are small, cold, and airless. Their surfaces offer no breathable atmosphere, but they do offer solid ground. In principle, an airless moon can host a sealed habitat more easily than a deep atmosphere can, because a habitat can sit on rock rather than float in gas. The main hazards then return to vacuum, radiation, and cold, which can be managed with engineering and power. This does not make survival easy, but it defines it more clearly. In this region of the journey inward, Uranus serves as a quiet example of an outer planet that looks gentle through distance, yet remains inaccessible to the human body. Its atmosphere is unbreathable. Its pressure increases without a surface boundary. Its cold is severe at the top, and its deeper layers become crushing and hot. Survival there is possible only in a technological enclosure held steady against a slowly changing environment. The planet's pale, calm appearance remains real. So does the strict physics that keeps it out of reach for unprotected life. Saturn's realm begins with its vast gravity and its wide magnetosphere, and it is visually defined by rings that stretch outward in a thin, bright plane. Yet the rings are not a safe surface. They're an enormous collection of countless particles, from fine grains to house-sized chunks, each following its own orbit. The space within and near the rings is filled with moving debris that can be beautiful to see and dangerous to cross. Saturn itself is a gas giant, and like the other giants, it does not provide a solid ground where a human can stand. Its atmosphere deepens continuously, becoming denser, hotter, and more pressurized with depth. In this region, survival depends on staying in protected space and managing hazards that come from both the planet's radiation environment and the ring system's dynamics. In the open space near Saturn, vacuum remains the immediate limit for unprotected life. A human exposed directly cannot breathe and cannot maintain normal bodily function without pressure. With a sealed suit or spacecraft, survival becomes a question of life support, duration, and power. Sunlight is stronger here than at Uranus and Neptune, but still weaker than near Earth, and heating demands remain significant. Solar power becomes more practical than in the far outer system. Yet long missions still benefit from internal power sources and robust thermal systems because the environment remains cold and because energy needs are continuous. Saturn's magnetosphere shapes a region where charged particles are guided and trapped. A magnetosphere is formed when a planet's magnetic field interacts with the solar wind. Saturn's magnetic field is strong, though weaker than Jupiter's, and it creates radiation belts that can expose spacecraft and living beings to elevated particle levels. Compared with Jupiter, Saturn's radiation environment is generally less extreme, but it remains significant. In particular locations, particle flux can be high enough to damage electronics and increase radiation dose for humans. The risk depends on orbital path, altitude, and the time spent within certain zones. Shielding can reduce exposure, and mission planning can avoid the worst regions, but the hazard remains part of Saturn's domain. The ring system adds a different kind of threat. The rings are thin in vertical thickness but wide in radial extent. Their particles move at high speed in orbit around Saturn. Relative velocities between nearby ring particles are often modest because they share similar orbits, but a spacecraft passing through the ring plane at the wrong angle could encounter particles at dangerous relative speed. Even small particles can damage surfaces at high speed. Larger particles would be catastrophic. For this reason, safe navigation near Saturn requires careful path selection. Spacecraft missions that have explored Saturn approach with precision, often crossing the ring plane at locations where particle density is low or avoiding the densest rings entirely. From a survival perspective, the rings are not a place where a human could exist without a protected habitat. The ring plane is vacuum, cold, and filled with moving material. A person in a suit could survive only as long as life support lasts, and only if the suit is not punctured. Even a small impact could compromise pressure. For longer survival, a habitat would need to be placed at a stable location on a solid body, such as one of Saturn's moons, rather than within the rings themselves. The rings remain a zone to observe and pass through carefully, not a zone to inhabit. Saturn's atmosphere begins as a broad cloud layer of hydrogen and helium with trace gases. It is unbreathable and far too cold for unprotected life. Even if pressure at the top of the atmosphere could be similar to Earth's at some altitude, the composition does not provide oxygen. A human would still need a sealed breathing system. As depth increases, pressure rises steadily. There is no sharp boundary where one could land on a surface. Any craft that descends must either maintain buoyancy at a chosen altitude or continue downward. If it continues downward, it encounters pressures that quickly exceed the strength of ordinary structures. Temperature rises as well, eventually becoming high enough to damage materials and destroy electronics. The idea of surviving within Saturn's atmosphere is therefore tied to floating platforms. A craft could in principle remain at an altitude where pressure is near Earth-like and where temperatures are less extreme than in deeper layers. Yet even in such a zone, the atmosphere remains chemically unsuitable for breathing, and the environment is windy and dynamic. Saturn's atmospheric circulation includes bands of fast winds and storms, including large-scale systems and periodic events that can disturb wide regions. A floating habitat would need active control to maintain position and altitude, as well as strong resistance to shear and turbulence. Without that control, drift and descent would bring increasing pressure and eventual structural failure. Saturn's gravity is strong enough to shape trajectories sharply. A spacecraft must manage orbital energy carefully for human survival. This matters because it influences how long a mission can remain in safe orbits without excessive fuel use. It also affects the consequences of an error. A small navigational mistake can lead to a trajectory that intersects dangerous regions, such as deeper radiation zones or the planet itself. In a distant environment where rescue is slow, precision and redundancy become survival factors. Saturn's moons change the practical picture. Several large moons orbit the planet, including Titan, which has a thick atmosphere, and many icy moons with solid surfaces. These moons offer places where a human habitat could rest on ground rather than float in a giant atmosphere. They remain cold and airless in most cases, and Titan's air is not breathable, but a solid surface allows structures, shielding, and resource use. For example, ice can provide water and radiation shielding, and rock can provide building material. A habitat on a moon can be buried or covered to reduce radiation exposure. These options do not make survival easy, but they make it definable. Saturn itself remains an environment where survival is almost entirely dependent on avoiding descent and avoiding prolonged exposure to hazardous zones. If the focus is strictly on Saturn as a planet, the survival picture remains narrow. Unprotected survival is essentially none because there is no breathable air and pressure conditions are not compatible with the body. Protected survival in the upper atmosphere is possible only if a craft can float and maintain stability. And even then, it depends on life support systems rather than the planet's conditions. Deeper survival is cut short by increasing pressure and heat. In orbital space, survival is possible within spacecraft or suits, limited by life support and radiation exposure. Near the rings, survival depends on avoiding impacts and maintaining suit integrity. Across these cases, Saturn does not offer natural refuge, but it does offer a complex environment in which the major threats are identifiable vacuum, radiation, cold, orbital debris, and pressure gradients. Saturn's domain is therefore a place where beauty and hazard coexist calmly. The rings glow softly, yet each particle is a moving object with mass and speed. The atmosphere appears smooth from afar, yet it hides winds, cold, and layers that become crushing. The magnetosphere is invisible, yet it shapes radiation environments that matter to living bodies. Survival within Saturn's realm is possible only inside engineered protection, and survival time is set by the durability of that protection and the ability to navigate a region where the most dangerous features are not visible to the eye but are present in physics and motion. Jupiter's presence dominates the outer solar system with mass, motion, and radiation. It is the largest planet, and it holds a powerful magnetic field that shapes an enormous magnetosphere. Around it, space becomes a region where energetic particles are trapped and accelerated, creating radiation belts that are among the harshest environments for spacecraft and living tissue anywhere outside the Sun's immediate reach. Jupiter itself is a gas giant, with no solid surface and an atmosphere that deepens into pressure and heat beyond any place a human body can endure. In this region, survival time is shortened not only by vacuum and cold, but by radiation that can become intense enough to damage unprotected life quickly and to overwhelm electronics over relatively brief spans. In the space near Jupiter, unprotected survival in vacuum remains brief. A person exposed directly cannot breathe and loses consciousness quickly. A suit or spacecraft can maintain pressure and provide oxygen, extending survival from minutes to hours and beyond depending on resources. Yet near Jupiter, radiation becomes a dominant risk even for protected systems. The planet's magnetic field captures charged particles from the solar wind and from volcanic activity in the Jovian system, especially from the moon Io, which supplies large amounts of material into Jupiter's magnetosphere. These particles become trapped and form belts that can expose objects moving through them to intense radiation. Radiation here is not one simple field. It varies with distance from the planet, with position relative to Jupiter's magnetic equator, and with time as the solar wind changes. The inner belts are the most intense. A spacecraft passing through them can receive a high dose, and electronics can suffer errors, degradation, and eventual failure. For a human, the main concern is damage to cells, especially in sensitive tissues. High radiation dose can cause acute radiation sickness, and can be lethal if extreme. Even lower doses increase long-term cancer risk. Near Jupiter, the exposure rate can be high enough that time spent unshielded becomes dangerous in short periods, and time spent with limited shielding remains a serious constraint. Shielding can reduce radiation, but it brings trade-offs. Dense materials such as water, polyethylene, and certain metals can help absorb or slow charged particles. A habitat could also use local water ice as shielding if stationed on or near a moon, but in orbit or in transit. Mass is expensive. The stronger the shielding, the heavier the craft, and the more difficult it becomes to launch, maneuver, or keep stable. For this reason, missions near Jupiter are planned carefully to limit exposure, and any human mission would require both heavy shielding and deliberate choice of orbits that avoid the most intense zones. Jupiter's moons provide some of the most compelling environments for science, but they also complicate survival. Io is volcanic and lies deep within the radiation belts. Europa, though an icy world with an ocean beneath its surface, also lies within strong radiation zones. Ganymede has its own magnetic field, which creates a small magnetosphere inside Jupiter's larger one, yet it is still bathed in Jovian radiation. Callisto lies farther out and experiences less intense radiation, making it comparatively safer as a potential base location. This gradient shows that within Jupiter's realm, distance is survival. The farther a habitat remains from the inner belts, the lower the radiation flux tends to be. Even then, protection remains necessary. Jupiter's atmosphere is unbreathable, made mostly of hydrogen and helium with traces of other gases. Cloud tops are cold and windy. Great storms churn across the planet, including long-lived systems such as the Great Red Spot. Yet these storms are not the primary barrier to human survival. The primary barrier is that there is no surface and no breathable environment. A human could not stand anywhere. A human could only float within the atmosphere in a craft, and that craft would have to withstand wind shear, lightning, turbulence, and changing pressure. If descent into the atmosphere continues, pressure rises steadily. At some altitude, external pressure becomes similar to Earth's at sea level, but the gas composition remains lethal to breathe. Deeper down, pressure climbs into tens of times Earth's surface pressure, then hundreds, then far beyond. Temperature rises as well. At depth, Jupiter's atmosphere becomes a hot, dense fluid. Any craft would be crushed long before reaching the deeper interior. The notion of surviving on Jupiter as though it were a landable world is therefore physically misplaced. Survival is limited to the thin region of space around it, or, at best, to controlled floating at high altitude, and even that is constrained by radiation and atmospheric violence. Gravity at Jupiter is also strong. It shapes trajectories and raises the speed of any object falling toward the planet. This increases the difficulty of atmospheric entry and makes escape more demanding. It also influences the speed of orbiting spacecraft, which can affect radiation exposure because time spent in certain regions may be hard to reduce while maintaining a stable orbit. Fast orbital motion does not remove exposure. It only spreads it differently across time. A mission design must account for where the radiation belts are strongest and how often the craft passes through them. Thermal conditions near Jupiter also require care. In space, temperatures can swing depending on sunlight and shadow. Near Jupiter, eclipses by the planet and by its moons can create repeated transitions between sunlight and darkness, stressing materials and systems. Yet compared with the radiation, thermal cycling is usually the more manageable constraint. It can be engineered with insulation and radiators. Radiation can be reduced but not eliminated without heavy protection or avoidance. Survival time in Jupiter's region therefore has several layers. In open space far from Jupiter, the basic limit without protection remains minutes because of vacuum. With a suit or spacecraft, survival can extend to hours and days depending on supplies. As a craft moves into Jupiter's radiation belts, survivability becomes dominated by shielding and exposure time. In the inner belts, radiation can become dangerous very quickly, making unshielded exposure potentially lethal within a short span. Even with shielding, time becomes limited unless the shielding is very strong. For long-duration human presence, the practical approach would favour locations farther from Jupiter's most intense belts, such as the region near Callisto, where radiation levels are lower, though still higher than in Earth's neighbourhood. Jupiter therefore acts as a harsh outer barrier not by wind alone, not by cold alone, but by the combination of deep atmosphere and intense trapped radiation. The planet's magnetosphere is vast and invisible, yet it defines safe and unsafe zones around the giant. The atmosphere is grand and layered, yet it offers no ground and no breathable refuge. The moons provide scientific fascination, yet many lie in radiation that makes surface work difficult without heavy protection. In the calm framing of survival, Jupiter is a reminder that the solar system contains environments where the strongest dangers are not always the ones that can be seen. They are the energetic particle fields and deep pressure gradients that persist, quietly, and that set strict limits on how long any unprotected or lightly protected human presence could endure. Between Mars and Jupiter, the solar system opens into a broad region often called the asteroid belt. It is not a dense field of tumbling rocks close together. It is a wide zone where objects are separated by great distances, orbiting the Sun in paths shaped by gravity and by the long history of planetary formation. The belt contains bodies ranging from dust grains to large asteroids, including the dwarf planet Ceres, yet most of the volume is empty. In this region, survival is not defined by weather, clouds, or ground-level pressure. It is defined by exposure to vacuum, by temperature swings in sunlight and shadow, and by the integrity of whatever system provides air, warmth, and protection. In open space within the asteroid belt, the first survival limit remains the same as anywhere outside an atmosphere. Without protection, a human cannot breathe and cannot maintain internal pressure. Oxygen deprivation begins immediately. Consciousness fades quickly. The body's fluids begin to behave abnormally in low pressure, and the risk of fatal injury becomes certain. In this sense, the asteroid belt does not introduce a new kind of unprotected survival limit. It is still measured in minutes at most, and practical function ends sooner. The belt simply provides a long region where this vacuum reality remains constant, and where rescue is less immediate than near Earth. Temperature conditions in the asteroid belt differ from the deep outer system. Sunlight is stronger than it is near Jupiter and beyond, yet still weaker than near Earth. More importantly, the environment is dominated by direct sunlight and deep shadow rather than by any buffering atmosphere. A surface in sunlight can heat, while a surface in shadow can cool sharply. Without air, there is no convection to spread warmth. This creates large temperature contrasts across the same body and across the same day. An astronaut in a suit is insulated from direct space temperature, but the suit still must manage heat input from the sun and heat loss by radiation. In sunlight, surfaces can overheat. In shadow, they can cool strongly. Thermal control systems must respond to these changes steadily, keeping the body and equipment within safe ranges. The asteroid belt also introduces a quiet hazard from impacts. Space contains micrometeoroids, tiny particles moving at high speed relative to any given object. In a wide region like the belt, these particles remain sparse, yet over long periods they are a constant background. A suit or spacecraft relies on pressure containment. A small puncture can cause air to escape. A robust design uses multiple layers, self-sealing materials, and internal redundancy. Still, The risk remains because any pressure loss becomes quickly dangerous. For a person, the most immediate threat is not freezing or burning, it is the loss of pressure and oxygen. The suit becomes the environment, and the suit's failure becomes the end point. Asteroids themselves offer solid surfaces, but they do not offer breathable atmospheres. Most are too small to hold significant air. Their gravity is weak, often far below Earth's. This affects movement and safety. A person stepping onto an asteroid is not truly stepping. A small push can send the body drifting away from the surface. Anchoring and careful motion become necessary. Tools must be secured. Dust and small rocks can float and cling. Even with a suit, the environment demands slow, deliberate action because a fall or slip is not the same as on Earth. It can become a slow, uncontrolled drift, with no air resistance to stop it, and no quick way to regain contact without propulsion or tethering. Weak gravity also affects long-term health. Prolonged low gravity leads to loss of muscle and bone density, changes in fluid distribution, and other physiological effects. For the survival times measured in minutes or hours, these effects are not the main limit. For months or years, they become serious. A habitat in the asteroid belt, if meant to support humans long-term, would likely need artificial gravity through rotation or other methods. This adds complexity but is not beyond physical possibility. The key remains that the belt offers solid material and vacuum, so a habitat can be built on or within rock, but it must provide the full set of life support conditions internally. The asteroid belt is also a region of resources. Many asteroids contain metals, silicates, and carbon-rich compounds. Some contain water bound in minerals or present as ice in protected regions. These materials could, in theory, support construction, radiation shielding, and fuel production. Water can be used for drinking, for oxygen production, and as a radiation shield, metals can be refined for structural components. Yet resources do not equal habitability. Extracting them requires energy, machinery, and time. It also requires safe work conditions in vacuum. The resource richness of asteroids therefore matters mainly for the potential of long-term habitats, not for unprotected survival time. Radiation in the asteroid belt is lower than near Jupiter's intense belts, but it remains higher than on Earth's surface because there is no thick atmosphere and no strong magnetic shield like Earth's. Solar particle events can deliver bursts of radiation. Galactic cosmic rays provide a constant background. A short exposure in a suit may be dominated by pressure and oxygen limits rather than radiation dose. But for longer stays, radiation becomes significant. A habitat can reduce exposure by using thick shielding, often best achieved by burying the habitat under regolith or building it within excavated rock. In this way, the belt's solid bodies can become protective rather than merely exposed. The question of survival time in the asteroid belt therefore depends on the level of protection. Unprotected survival remains brief because vacuum dominates. A pressure suit extends survival as long as it provides oxygen, removes carbon dioxide, maintains pressure, and manages heat. Typical suit operations also depend on water, battery power, and system durability. With a spacecraft, survival can extend further if the craft provides larger life support capacity and better shielding. With a habitat built into an asteroid, survival could in principle extend for long periods, limited by supplies, recycling systems, power generation, and maintenance. In that case, the environment outside remains lethal, but the pocket inside remains stable as long as engineering holds. The belt also provides a calm contrast to the giant planets. There is no crushing atmosphere overhead, and no single dominant radiation field like Jupiter's inner belts. Instead, there is openness, vacuum, sunlight, shadow, and scattered rock. The dangers are simple and persistent. Loss of pressure and oxygen ends life quickly. Temperature extremes stress equipment and bodies without proper control. Radiation accumulates over time. Impacts threaten suit integrity. Weak gravity changes movement and long-term physiology. These are steady facts, not dramatic events. In the story of surviving the solar system, the asteroid belt acts as a region where the survival problem returns to fundamentals. It is not a place with an air that kills. It is a place with no air at all. It is not a place with crushing pressure. It is a place with almost none. It is not a place where heat comes from a thick greenhouse atmosphere. It is a place where sunlight and shadow create sharp contrasts, and where the body survives only within the thin engineered boundary of a suit or habitat. In this calm emptiness among scattered stones, survival is measured by the quality of protection and the persistence of life support systems, and by nothing else. Mars lies inward of the asteroid belt as the first planet that resembles Earth in the simplest outline. It is a rocky world with a day-night cycle similar in length to Earth's, and seasons driven by axial tilt. It has mountains, valleys, polar caps, and dust that moves with wind. Yet resemblance in silhouette does not mean similarity in survival. Mars has an atmosphere, but it is extremely thin compared with Earth's, and it is not breathable. Its surface is cold on average, and it is exposed to higher radiation than Earth's surface because the atmosphere and magnetic protection are weak. In this region, survival time depends on whether the human body is exposed directly to the Martian environment or sheltered behind pressure and life support. The Martian atmosphere is composed mostly of carbon dioxide, with smaller amounts of nitrogen and argon, and traces of other gases. The pressure at the surface is typically less than 1% of Earth's sea level pressure. This low pressure creates an immediate problem for unprotected humans. The body requires not only oxygen, but also sufficient pressure to keep water in liquid form and to allow lungs to exchange gases. On Mars, the pressure is too low for normal breathing and circulation. A person without a pressure suit would not be able to breathe usable oxygen because there is essentially none available, and the pressure would be too low to support normal lung function. Loss of consciousness would occur quickly as oxygen in the blood falls. In addition, low pressure affects body fluids. At sufficiently low pressure, water begins to boil at body temperature. The Martian surface pressure is near a boundary where this becomes a concern for exposed tissue. The exact response depends on temperature and on local pressure, which varies with altitude and weather. What is clear is that the body cannot remain stable without pressurization. Skin and tissues provide some containment, but the absence of adequate external pressure leads to rapid physiological collapse. Even before cold becomes dominant, the absence of breathable air and pressure makes unprotected survival very brief. Cold then adds its own steady pressure. Mars is farther from the sun than Earth, and it receives less sunlight. Its thin atmosphere provides little greenhouse warming and little ability to spread heat. As a result, temperatures can drop very low, especially at night and at higher latitudes. In daylight, near the equator, temperatures can rise above the freezing point of water at times, but the low pressure means liquid water is unstable at the surface, tending to evaporate or freeze. For a human, cold exposure without protection would quickly worsen injury and shorten survival, but the first failure remains lack of pressure and oxygen. Mars also has wind, but the wind is not strong in the way it is on Earth in terms of force. The thin air carries little momentum, yet Mars winds can still lift and transport dust, and dust can become the main environmental factor for equipment and for solar power systems. Planet-wide dust storms occur, and even more common are regional and local storms that reduce visibility and change surface heating. A dust-filled sky reduces sunlight reaching the surface and can lower temperatures. Dust can cling to equipment, wear surfaces, and contaminate moving parts. For a pressure suit, the main immediate threats remain pressure integrity and thermal control, but dust affects long-term reliability and comfort. Radiation is a larger long-term hazard on Mars than on Earth. Earth's thick atmosphere and global magnetic field reduce radiation exposure at the surface. Mars lacks a strong global magnetic field today and has only a thin atmosphere. This means that cosmic rays and solar energetic particles reach the surface more easily. Over short periods, a person in a suit may not receive a lethal dose, but over months, cumulative exposure becomes significant. Solar particle events can also produce sudden increases in radiation. Shelters on Mars often need additional shielding, such as thick walls or coverage by soil, to reduce dose for long stays. The Martian surface offers gravity that is about 1/3 of Earth's. This is less extreme than the microgravity of orbit, but it still affects the body over time. Long-term low gravity can lead to muscle and bone loss, though less rapidly than in near-zero gravity. For survival measured in minutes, gravity is not the main factor. For survival measured in years, it becomes part of the health burden. A long-duration human presence would need exercise, medical monitoring, and possibly rotating habitats to provide artificial gravity for part of the day. With protection, the survival picture changes dramatically. A pressure suit provides air, pressure, temperature control, and mobility. On Mars, a suit must be robust and reliable because the outside environment cannot support life. Even a small leak can become dangerous. The suit must also manage heat. Despite the cold environment, physical work produces heat, and the suit must reject excess heat through radiators and internal cooling systems. At night or in shadow, the suit must supply heat to prevent hypothermia. The thin Martian atmosphere provides little convective cooling, so thermal management remains similar to vacuum in many respects, with radiation as the main heat exchange. A pressurized habitat provides a more stable solution. Inside, pressure and oxygen can be maintained near Earth-like levels, temperature can be regulated, water and food can be stored and recycled. The limiting factors become power, supplies, recycling efficiency, and maintenance. On Mars, solar power is feasible, though reduced compared with Earth, and dust can interfere with it. Nuclear power offers more consistent output. A habitat can use the Martian environment for shielding by burying living spaces under soil or building within natural caves or excavated spaces. Such shielding reduces radiation and stabilizes temperature. In this way, Mars becomes a place where survival can extend from minutes to months and years, not because the planet is naturally hospitable, but because its solid surface allows construction and shielding. The question of how long a human could survive on Mars without protection is therefore answered mainly by physiology. Loss of breathable air and pressure leads to rapid incapacity. Cold worsens the situation. The time is brief. With a suit, survival extends to the duration of suit supplies and integrity, which can be hours. With a habitat, survival extends to the duration of supplies, recycling, and power, which can be long. The planet's thin atmosphere offers some modest protection from micrometeoroids compared with vacuum, but it is not enough to make exposure safe. Mars therefore stands as the closest planet in the solar system to a world where human survival is imaginable on the surface with technology, and where building a stable environment is physically plausible. It is not a place where the body can endure unaided, Its air cannot be breathed, its pressure is too low, its cold is persistent, and its radiation exposure is high. Yet it is a place with ground, with water ice, with carbon dioxide that can be used in chemical processes, and with sunlight that can be harvested. In the calm spectrum of the solar system, Mars marks a transition from the giants and vacuum regions toward a rocky world where survival begins to depend less on avoiding an atmosphere and more on replacing it with a controlled one. Near Earth, the solar system becomes familiar in shape, yet survival outside the atmosphere remains as strict as anywhere else. Earth's orbital neighborhood is a region where a person can see the planet's blue curve below and still face the same immediate constraints of vacuum, temperature control, and radiation. Low Earth orbit is not a gentle extension of the surface. It is open space close to a living world, and that closeness can hide how quickly the body fails when pressure and breathable air are removed. In this region, survival is defined by the boundary between Earth's atmosphere and the vacuum above it, and by the thin layer of technology that allows humans to cross that boundary for limited time. In orbital space, pressure is effectively absent. A human without a sealed suit or a pressurized vehicle cannot breathe and cannot maintain stable internal function. The lungs cannot draw in air because there is none, and oxygen in the blood falls quickly. Consciousness fades in a short span as the brain is deprived. At the same time, the loss of external pressure allows gases and water in exposed tissues to behave abnormally. Skin and tissue prevent a sudden violent rupture, but swelling and injury begin. The critical limit remains oxygen and pressure rather than cold. In orbit near Earth, unprotected survival is still measured in minutes at most, and the time of useful action is shorter. This is a constant physical reality of vacuum, regardless of how close the orbit is to home. Temperature in low Earth orbit is shaped by sunlight and shadow rather than by air temperature. In sunlight, a surface can heat strongly because it absorbs solar energy directly. In shadow, a surface cools by radiating heat to space. Because there is no air for convection, heat does not move away from the body by wind. It moves mainly by radiation and by conduction through whatever the body touches. A suit or spacecraft must manage this balance. It must prevent overheating in sunlight and prevent excessive cooling in shadow. The same object can experience rapid changes in heating as it passes into and out of Earth's shadow during each orbit. These cycles can occur repeatedly, creating a rhythmic pattern of thermal stress on materials and systems. Earth's presence changes the radiation environment in a complex way. The planet's magnetic field forms a magnetosphere that deflects many charged particles from the solar wind and guides them around Earth. This magnetic field and the atmosphere together protect the surface from much of the high-energy particle flux that exists in space. In orbit, that protection is reduced. The atmosphere is thinner, and the shielding effect of air is less. The magnetic field still helps, but the details depend on orbit altitude and inclination. Some regions of low Earth orbit pass through areas where trapped particles are more intense, such as parts of the Van Allen belts, and the overall radiation dose can be higher than on the ground. One notable region is the South Atlantic anomaly, an area where the inner radiation belt comes closer to Earth's surface because of the geometry of the magnetic field. Spacecraft passing through this region experience increased exposure to energetic particles, and instruments may be affected. For humans in orbit, this contributes to the overall radiation dose and requires monitoring and operational planning. The effect is not usually lethal in a single pass, but repeated exposure over weeks and months becomes significant. Radiation in orbit also includes cosmic rays, high-energy particles that come from beyond the solar system. Earth's atmosphere blocks much of this at the surface, In orbit, more of it reaches the body. Solar particle events add another layer. During periods of strong solar activity, the Sun can release bursts of energetic particles that increase radiation levels. In orbit, protection depends on shielding and on the ability to take shelter within more protected parts of a spacecraft. A spacesuit provides limited shielding. A spacecraft provides more, especially if its walls are thick and if stored water and supplies are arranged to add protection. Even then, radiation remains a cumulative risk, shaping how long people can safely remain in orbit and how missions are planned. Survival in low Earth orbit is therefore dominated by engineering integrity. A pressure suit must maintain stable internal pressure, provide oxygen, remove carbon dioxide, control humidity, manage temperature, and protect against micrometeoroids and debris. A suit is also a life support system with limited reserves. Oxygen supply and carbon dioxide removal capacity set time limits. Cooling systems require power and circulating fluids. Batteries set the duration of independent operation. Any failure in pressure containment becomes immediately dangerous. This is why redundancy, careful design, and constant monitoring are central. The suit is not a simple garment. It is a small spacecraft around a human body. Micrometeoroids and orbital debris are more prominent risks near Earth than in many deeper regions of space, because human activity has placed many objects in orbit. Natural micrometeoroids exist everywhere, but near Earth there is an additional population of human-made debris fragments of old satellites, spent rocket stages, and tiny particles created by collisions and wear. These objects move at high speed relative to one another. Even a small fragment can carry enough kinetic energy to puncture surfaces. Space stations and spacecraft use shielding and tracking to reduce risk. A spacesuit is more vulnerable. The environment is therefore not only vacuum and radiation, but also a traffic zone that must be managed with careful operational choices. Low Earth orbit also introduces physiological changes that affect survival over longer times. Microgravity is the condition of very low effective gravity experienced in orbit because the spacecraft and its occupants are in continuous free fall around Earth. In microgravity, the body's fluids shift upward, altering circulation and pressure in the head. Muscles and bones weaken without regular loading. The balance system adapts to weightlessness and then must readapt when gravity returns. These effects build over days and weeks. They are not the immediate limit for exposure outside a suit, but they define the longer-term cost of living in orbit. Astronauts counter them with exercise, careful nutrition, and medical monitoring, but the burden remains. Survival in orbit is possible for months, yet it is not effortless for the body. The orbital environment is also shaped by the thin upper atmosphere that still exists at these altitudes. Though it is far too thin to breathe, it creates drag on objects in low orbit. Drag gradually lowers orbital altitude unless propulsion raises it. This means that long-term presence in low Earth orbit requires occasional reboost. Space stations must manage this with engines and fuel. Debris can slowly change orbits due to drag, and re-entry risk becomes part of the orbital life cycle of objects. For survival, this matters because maintaining a stable orbit requires planning and resources. Even near Earth, the environment demands continual management. The boundary between low Earth orbit and the upper atmosphere is also where re-entry heating becomes critical. A spacecraft returning to the surface must pass through denser air at high speed, compressing the air and generating intense heat. Heat shields and controlled trajectories are required. This does not affect survival while already in orbit, but it shapes the reality that orbit is not a state that can be entered and left casually. It requires robust systems in both directions. Within this region, Earth remains visible as a safe world below. Yet the contrast is the defining fact. A person can be a few hundred kilometers above breathable air and still be separated from it by the most lethal conditions in space. Survival time in orbit without protection remains brief, limited by vacuum and pressure loss. Survival time with protection depends on life support capacity, radiation exposure, thermal control, and the management of debris risk. The environment is calm in appearance, with slow motion and quiet horizons, but it is strict in physics and unchanging in its demands. Low Earth orbit therefore serves as a hinge in the solar system story. It is the first place where humans have already lived and worked beyond Earth's atmosphere, proving that survival is possible with technology. At the same time, it demonstrates that closeness to Earth does not reduce the fundamental dangers of space. It only shortens travel time back to safety. The boundary remains clear. Below, Earth's air and pressure support life continuously. Above, a sealed system must supply every breath, hold every degree of warmth, and shield every vulnerable cell against a thin but persistent particle environment. In this calm, near space, survival becomes the ongoing maintenance of a small artificial world, held steady while the planet turns slowly beneath. Earth is the only planet in the solar system where humans survive long-term without sealed technology. This is not because Earth is gentle in every way, but because it provides the basic physical conditions that human biology requires. Air contains oxygen in a usable concentration. Atmospheric pressure supports breathing and keeps water stable as a liquid. Temperatures, while variable, often remain within ranges that living tissue can tolerate. Water is abundant and accessible. Gravity is strong enough to support normal body function. Earth's magnetic field and atmosphere reduce radiation exposure compared with open space. These conditions work together as a complete system. Survival on Earth is therefore not a special case of endurance. It is the baseline from which all other planetary survival limits are measured. Breathing on Earth works because air pressure is sufficient to push oxygen into the lungs, and because oxygen partial pressure, the share of atmospheric pressure contributed by oxygen stays high enough for blood to carry oxygen efficiently. At sea level, pressure is about 1 atmosphere, and the oxygen fraction is roughly 1/5. This combination supports normal respiration. At higher altitudes, pressure drops and oxygen availability falls, and humans can suffer altitude sickness. This shows that even on Earth, pressure matters. Yet Earth offers wide regions where pressure remains close to the body's needs. The atmosphere does not need to be carried in tanks, and the lungs do not need mechanical assistance in normal conditions. Earth's atmosphere also provides thermal buffering. Air moves heat by convection, spreading warmth from sunny regions and mixing layers. Water vapor, carbon dioxide, and other greenhouse gases trap some heat, preventing Earth from cooling to extreme temperatures during the night and keeping the planet's average temperature within a range that allows liquid water. Clouds reflect sunlight and also trap heat. Oceans store large amounts of thermal energy and release it slowly, moderating seasonal and daily changes. These mechanisms create a climate system that can be harsh in local extremes, but remains broadly compatible with life. The key is not comfort. The key is that the environment allows stable body temperature through ordinary shelter and clothing rather than through full pressure suits. Water on Earth exists in all 3 common phases: ice, liquid, and vapor. Most importantly, it exists widely as liquid. Liquid water is essential for human survival and for all known life. It supports metabolism, circulation, and chemical stability. Earth's pressure and temperature allow water to remain liquid at the surface over vast areas and long times. This is not guaranteed on other planets. Low pressure makes liquid water unstable. Extreme cold freezes it. Extreme heat boils it. Earth provides a long-term balance that keeps rivers flowing, oceans stable, and groundwater available. Survival on Earth is therefore supported not only by air, but by the continuous presence of liquid water. Earth also provides chemical diversity that supports food. Plants grow using sunlight, water, and carbon dioxide. Animals and other organisms form food webs. Humans survive not by extracting energy directly from sunlight, but by living within a biosphere that captures and stores energy and biological matter. This allows long-term survival without carrying all resources in a vehicle. It also supports the possibility of living without constant industrial systems. Even in harsh regions, humans can sometimes survive by using local ecology and stored supplies. This is the opposite of most other planetary environments, where life support must be entirely engineered. Gravity on Earth supports the body's structure and function. Muscles and bones are adapted to one Earth gravity. In microgravity, muscle and bone loss occurs without constant countermeasures. On worlds with much lower gravity, similar long-term issues may arise, though the details depend on how low the gravity is and how long exposure lasts. Earth's gravity also keeps the atmosphere bound and supports stable weather patterns. It affects how blood circulates, how balance works, and how bodies develop and maintain strength. Survival without medical intervention is most natural at the gravity in which the body evolves. Radiation protection is another part of Earth's baseline. The atmosphere absorbs much of the sun's ultraviolet radiation and blocks a large fraction of cosmic rays. Earth's magnetic field deflects many charged particles from the solar wind and guides them toward polar regions, where they can create auroras. This does not eliminate radiation. Natural background radiation exists from cosmic rays and from radioactive elements in Earth's crust. Yet compared with open space or thin atmosphere worlds, Earth reduces exposure dramatically. This protection becomes especially important during solar particle events, which can raise radiation levels in space. On Earth's surface, the atmosphere and magnetic field lessen the impact. Earth's surface pressure also prevents the rapid physiological failures that occur in vacuum or thin atmospheres. Body fluids remain stable. Water does not boil at body temperature. Breathing works normally. A person can remain conscious, active, and healthy without a pressure vessel. This single fact explains much of the difference between Earth and Mars, or Earth and the Moon. Pressure is not a subtle factor, it is a defining one. On Earth, pressure is provided for free by the atmosphere. Even so, Earth is not universally safe. Temperature extremes can be lethal. Heat can overwhelm the body's ability to cool itself through sweating, especially when humidity is high. Cold can cause hypothermia when insulation and shelter are insufficient. Water can be scarce in deserts. Storms can destroy shelter. Disease and injury can end life without medical care. Yet these hazards exist within a context where the basic physical requirements are present. The body can still breathe. Water can still exist as liquid. Fire can still burn, allowing warmth and cooking. These are not small advantages. They are the reason survival on Earth can be indefinite in principle. In the context of the solar system, Earth serves as the reference point for all survival times. When other planets are described as offering survival for seconds, minutes, or hours without protection, it is because they lack what Earth provides continuously. When suits and habitats are described as extending survival, it is because they recreate, in miniature, the conditions Earth provides naturally: pressure, oxygen, temperature control, and protection from radiation. Earth is the only world where those conditions come from the environment itself. This baseline also clarifies what survival means. Survival is not only staying alive for a short time after exposure, it is maintaining normal bodily function without progressive damage. On Earth, the body can repair itself, rest, and continue. Food and water can be replenished from the environment. Social systems and technology can further extend survival, but they are not required for the simplest biological continuity. This makes Earth the center of the survival spectrum, the one world where human life can proceed without constant life support machinery. In this calm comparison, Earth's ordinariness becomes its greatest gift. It is not the largest planet, it is not the most dramatic, it is not the hottest, coldest, or most massive. It is simply the one world where air, pressure, water, and moderate temperature overlap in a stable way over deep time. That overlap is rare in the solar system, and it is the reason Earth is the single place where survival is not a countdown but a continuing state. The Moon lies close to Earth, yet it is one of the clearest reminders that distance does not equal safety. The lunar surface is airless. There is no breathable atmosphere, and there is no meaningful surface pressure. The ground is covered in fine dust and broken rock, and the sky is black even in daytime because there is no air to scatter sunlight. Temperatures swing widely between long days and long nights. Radiation reaches the surface more easily than on Earth because there is no thick atmosphere and no global magnetic shield. In this region, survival time depends almost entirely on technology. Without it, the Moon is as lethal as open space. In vacuum on the Moon, unprotected survival is brief. Breathing stops immediately, oxygen in the blood falls quickly, and consciousness fades. The body cannot function without the external pressure that keeps lungs operating normally and keeps water stable in the tissues. Exposure leads to rapid physiological failure. The first limit is not cold, because cooling in vacuum is slower than it would be in air. The first limit is oxygen deprivation and pressure loss. Even before hypothermia becomes severe, the brain lacks oxygen and normal circulation cannot continue. The Moon's surface therefore offers no meaningful unprotected survival interval beyond the short span set by vacuum. With a pressure suit, survival extends to the duration of life support. A suit must provide oxygen, remove carbon dioxide, manage humidity, control temperature, and protect against micrometeoroids. On the Moon, the suit's thermal system is especially important because of the extremes between sunlight and shadow. In direct sunlight, a surface can become hot because it absorbs solar energy and has little way to shed heat except by radiation. In shadow, surfaces can become extremely cold as they radiate heat away. A suit must keep the body near a stable temperature despite these swings. This requires insulation, circulating cooling fluid, radiators, and precise control. Battery power and consumables set the operational duration. The suit remains a small pressurized habitat wrapped around the body, and its endurance defines survival time during surface activity. The lunar day is long. One lunar day-night cycle lasts about a month in Earth time. That means a site on the Moon experiences roughly 2 Earth weeks of daylight, followed by roughly 2 Earth weeks of night. The surface temperature can rise high in sunlight and fall very low at night. These extremes challenge equipment and habitats. A habitat must maintain stable temperature during both phases. It may use insulation, heaters, and thermal storage. It may also choose locations near the poles where sunlight angles are low and where some regions receive near continuous light, while nearby craters remain in permanent shadow. These polar regions are scientifically important because permanently shadowed craters can preserve water ice. For survival planning, they also provide both advantages and challenges: possible access to ice for water and shielding, but also deep cold in shadowed zones. Radiation on the Moon is higher than on Earth's surface. Galactic cosmic rays reach the ground with less attenuation, and solar energetic particles can strike the surface during solar storms. A suit provides limited protection. A habitat can provide more, especially if it is shielded with layers of regolith, the loose surface material, or built into or covered by lunar soil. Water can also serve as shielding. The most practical strategy for long-term living is to increase shielding mass, because particle radiation is reduced as it passes through dense material. Without shielding, a long stay on the lunar surface would involve a rising cumulative radiation dose, with increased health risk over time. Micrometeoroids are another quiet hazard. The Moon lacks an atmosphere to burn up incoming particles. Small meteoroids strike the surface frequently, creating tiny impacts. Most are too small to threaten a human habitat directly, but they can puncture exposed equipment and wear down surfaces over time. A suit is vulnerable to puncture, and a habitat needs layered protection. Modern designs often include shielding systems that absorb impacts and operational plans that reduce time spent outside during high-risk periods. The risk is low at any given moment, but over long durations, it becomes part of the maintenance burden. The lunar dust itself introduces a practical survival complication. Lunar regolith is sharp and abrasive, produced by billions of years of micrometeoroid impacts that grind rock without weathering by air or water. The dust clings to surfaces through electrostatic effects and can infiltrate joints, seals, and machinery. It can irritate lungs if brought inside a habitat, and it can scratch visors and degrade materials. For survival, dust is not the immediate lethal factor, but it can cause equipment failure and health problems if not managed. Effective living on the Moon requires careful dust control through airlocks, suit cleaning systems, and habitat design that keeps abrasive particles out of critical mechanisms. Gravity on the Moon is about 1/6 of Earth's. This affects movement, balance, and long-term physiology. People can move with less effort, but they must also adapt to a different gait and to reduce traction. Over time, low gravity contributes to muscle and bone loss, though less severely than microgravity in orbit. Long-term lunar habitation would likely require exercise regimes, medical monitoring, and possibly rotating habitats to provide partial artificial gravity. For short excursions, gravity is mainly a matter of mobility and safety during surface work. Long-term survival on the Moon is therefore possible only in a controlled environment. A habitat must supply pressure, oxygen, temperature regulation, water, food, and waste management. It must manage power through long nights or find regions with extended sunlight. It must provide radiation shielding and safe shelter during solar particle events. It must handle dust, micrometeoroid impacts, and mechanical wear. These are complex requirements, yet they are definable. The Moon's solid surface makes construction possible. Materials can be used for shielding and building. Ice may provide water and oxygen in some regions. The challenge is that nothing is provided naturally in breathable, comfortable form. Unprotected survival remains brief because vacuum is absolute. Protected survival in a suit remains limited by suit life support and by the need to return to shelter before power, oxygen, and cooling resources are exhausted. Protected survival in a habitat can be extended indefinitely in principle if supplies and power are maintained, but in practice it depends on robust engineering, reliable energy, and continuous maintenance. The Moon therefore occupies a clear position on the solar system survival spectrum. It is close to Earth, yet it offers none of Earth's natural support. It is a place where survival becomes a steady engineering task, and where every hour of safety is held by seals, pumps, shields, and careful planning under a black sky. Venus lies inward of Earth as a planet of similar size and mass, yet its surface environment is among the most hostile in the solar system. The difference is not subtle. Venus is wrapped in a dense atmosphere made mostly of carbon dioxide, with thick clouds of sulfuric acid droplets and a surface pressure far higher than Earth's. Heat's extreme. The surface temperature remains hot enough to overwhelm ordinary materials and living tissue. In this region, survival time without extraordinary protection is extremely short, and the main causes are crushing pressure and intense heat rather than vacuum. Venus's atmosphere begins high above the surface with layers of cloud and haze. The upper atmosphere is thin compared with the crushing depths below, yet it remains unbreathable. There is no oxygen to support human respiration. Carbon dioxide dominates, with nitrogen present as a smaller component. The clouds contain sulfuric acid droplets, which are corrosive and hazardous to exposed equipment. At high altitudes, pressures can be lower and temperatures cooler than at the surface, but the air remains chemically unsuitable for breathing and can be damaging to lungs and eyes even if pressure were tolerable. Without a sealed breathing system and protective structure, survival is not possible. The defining danger of Venus is at the surface. Pressure there is about 90 times Earth's sea level pressure. This means that the force on any object is enormous. Human bodies are not adapted to such compression, even with breathable air. Such pressure would be lethal without a pressure-resistant enclosure. In addition, the gas itself is dense and hot. The surface temperature is around 460 degrees Celsius, maintained by a powerful greenhouse effect. The atmosphere traps heat so effectively that Venus remains hot both day and night. Venus rotates slowly, but the surface temperature does not swing widely with the day-night cycle in the way an airless world does. The dense atmosphere stores and circulates heat, keeping the surface in a continuous high-temperature state. Heat at this level damages living tissue rapidly, proteins lose their structure, and biological systems fail. Equipment also suffers. Many metals soften, lubricants break down, and electronics fail unless specially designed and insulated. A human in ordinary clothing would not survive even for a moment because the heat alone is lethal. A human in a pressure suit designed for vacuum would also not survive because the suit is not built for extreme external pressure and would be crushed, and because its thermal control system cannot reject heat to an environment that is already extremely hot. The environment outside would be the hotter reservoir, so cooling systems would lose their ability to shed heat. The suit would heat up rather than cool down. Pressure and heat act together. A structure that resists pressure must be strong, but high temperature weakens many materials and can degrade seals and joints. Any enclosure designed to protect life at Venus's surface would need thick walls, high-temperature materials, and a way to keep the interior cool. Even if the interior is insulated, heat would seep inward over time. The duration of survival would then depend on how long the enclosure can maintain acceptable internal temperature and pressure before heat overwhelms the system, or before mechanical failure occurs. This is why past landers on Venus operate only for limited times. The engineering problem is extreme. Venus's atmosphere also contains chemical hazards. Sulfur compounds and acidic droplets dominate the cloud layers. Near the surface, the atmosphere is very dry, but it can still be chemically reactive. Corrosion affects exposed metals and can degrade protective coatings. Wind at the surface is relatively slow compared with the winds at the cloud tops, but because the air is dense, even moderate winds can exert force. Higher up, winds can be very fast, and the super-rotating atmosphere carries clouds around the planet much more quickly than the solid body rotates. These dynamics matter for any platform trying to remain at a stable altitude. Survival on Venus therefore becomes a question of altitude and enclosure rather than a question of standing on the ground. There is a narrow region in the Venusian atmosphere, roughly around the altitude, where pressure becomes similar to Earth's sea level pressure, where temperatures are also far lower than the surface. In that band, the external pressure can be near Earth-like, which is an unusual and important fact. The temperature there is often described as moderate compared with the surface, though it can still be warm. The air is still unbreathable and the clouds contain corrosive acid droplets, so an unprotected human still cannot survive. Yet for engineering, this region is sometimes considered the most plausible for long-duration platforms because the pressure requirement is less severe than at the surface. A floating habitat in this altitude band would need a sealed interior with breathable air, and it would need a protective outer skin resistant to acid. It would also need systems to handle moisture, heat exchange, and long-term exposure to chemical corrosion. Buoyancy is possible because the dense carbon dioxide atmosphere provides lift for lighter gases. Even so, survival time would depend on the habitat's durability and on power for life support. This does not make Venus habitable. It makes one part of its atmosphere less mechanically crushing than the surface, offering a potential zone for sustained presence if technology is strong enough. From a strict survival perspective, however, any scenario without a sealed habitat remains short in the upper atmosphere. Pressure may be too low for normal breathing, and oxygen is absent. In the cloud layers, acid droplets add corrosive hazard. At the surface, heat and pressure end life immediately. A pressure suit alone cannot solve these combined constraints. A suit is designed to provide pressure in vacuum and to manage heat by radiating to cold space. On Venus's surface, the outside pressure is crushing and the outside temperature is extremely high, reversing the thermal gradient that suits depend on. The suit would be forced inward and heated from the outside. Survival becomes a matter of rigid enclosure, insulation, and active cooling, all of which require substantial mass and power. Venus also offers no easy relief through shade or night, because the greenhouse effect dominates. The planet does not cool meaningfully after sunset. The surface remains nearly constant in extreme temperature. This eliminates one of the few advantages that an airless world offers, where a person might choose a shadowed region for reduced heating, even though vacuum remains lethal. On Venus, heat is everywhere at the ground level. The atmosphere is thick enough to spread and retain energy, making conditions uniform in their hostility. Radiation at Venus's surface is less of a limiting factor than on Mars or the Moon because the thick atmosphere blocks much of the incoming cosmic radiation. This is one of the few protective qualities of Venus's air. Yet it does not help the body, because the same atmosphere and greenhouse conditions create the lethal pressure and heat. In the balance of hazards, Venus replaces vacuum and radiation with crushing pressure and heat. Survival remains impossible without heavy engineering. The practical survival conclusion is therefore clear. On Venus's surface, unprotected survival is effectively zero. A human cannot breathe, cannot maintain body temperature, and cannot withstand the pressure. With ordinary protective equipment, survival remains essentially none, because the equipment would fail under pressure and heat. Only a specialized high-pressure, high-temperature capable enclosure could provide any survival time, and that time would depend on how long the enclosure can resist crushing force and prevent heat from raising the internal temperature beyond safe limits. Higher in the atmosphere, the pressure becomes more manageable, but breathable air is still absent and acid clouds remain hazardous. So survival still requires a sealed, protected habitat. In the inner solar system, Venus stands as a powerful example of how a planet similar in size to Earth can become utterly different in surface conditions. Its thick carbon dioxide atmosphere and persistent greenhouse warming create a world where heat and pressure dominate every survival calculation. The planet offers no open-air refuge and no surface interval of tolerable conditions. Survival, if it occurs at all, exists only within engineered isolation from the environment, and on the surface the environment is so extreme that even that isolation is difficult to sustain for long. Mercury lies closest to the Sun among the planets, and it is an airless world with a surface that experiences some of the most severe temperature contrasts in the solar system. Mercury has no substantial atmosphere to store and redistribute heat. It has only a tenuous exosphere, a very thin scattering of atoms that does not behave like air. Without an atmosphere, Mercury cannot provide breathable gas, meaningful pressure, or protection from micrometeoroids and high-energy radiation. The planet is therefore similar to the Moon in its lack of air, yet it differs sharply in its proximity to the Sun, which raises surface heating in sunlight and increases exposure to solar radiation. In this region, survival time without protection remains brief because vacuum dominates, and longer survival depends on the ability of equipment to manage extreme heat in day and deep cold in night while remaining sealed against pressure loss. On Mercury, unprotected survival is cut short immediately by vacuum. There is no air to breathe and no pressure to keep bodily function stable. The same sequence occurs as in open space. Breathing stops, oxygen in the blood falls, and consciousness fades quickly. Swelling begins as pressure drops, and exposed fluids behave abnormally. The body cannot operate without a pressurized environment and a supply of oxygen. This sets a short maximum survival time, measured in minutes at most. Temperature extremes matter for materials and long-term exposure, but the first physiological limit remains lack of air and pressure. The Mercury day is long, because Mercury rotates slowly and orbits the Sun quickly. The time from one sunrise to the next at a given point on the surface is much longer than an Earth day. This means that a region can remain in sunlight for a long interval, and then remain in darkness for a long interval. During the day, the surface can become extremely hot. During the night, it can become extremely cold. Without air to move heat, the surface responds directly to sunlight and directly to darkness. A sunlit rock heats, a shadowed rock cools. This creates a planet where temperature is controlled primarily by direct radiation, rather than by atmospheric mixing. In direct sunlight, Mercury's surface temperatures can rise to several hundred degrees Celsius. In darkness, they can fall to well below freezing, reaching extremely low values. These extremes pose a major problem for survival in any habitat or suit because they stress materials and require active thermal management. A suit designed for spacewalks near Earth must already handle sunlight and shadow, but Mercury's sunlight is stronger, and the surface can radiate intense heat upward. A person standing near the sunlit surface would be exposed not only to direct solar energy, but also to infrared radiation from hot ground. Cooling systems would work harder, and heat rejection becomes more difficult if the environment around the suit is hot rather than cold. In shadow, the opposite problem appears. The surface becomes so cold that any unheated equipment cools rapidly by radiation. A suit or habitat must provide continuous heating to prevent freezing of critical systems. Batteries lose performance at low temperature, lubricants change viscosity, and materials contract. Repeated thermal cycles can cause cracking and fatigue. Long-duration survival on Mercury would require designs built for extreme thermal swings, robust insulation, and the ability to store or generate power continuously. Mercury's proximity to the Sun also raises radiation exposure. Solar ultraviolet and particle radiation are more intense closer to the Sun. Mercury lacks an atmosphere to absorb ultraviolet light, so the surface is exposed directly. A suit or habitat must provide shielding for ultraviolet and for high-energy particles. Solar particle events can produce bursts of radiation that increase risk. In deep space, a habitat can sometimes take shelter behind mass or within more shielded compartments. On Mercury's surface, shelter can be created by building within rock or by using regolith for shielding. A habitat placed inside a crater wall or beneath the surface would gain both radiation protection and thermal stability, because underground temperatures change less rapidly than surface temperatures. Mercury has a magnetic field, but it is much weaker than Earth's. It creates a small magnetosphere that interacts with the solar wind, but it does not provide broad surface protection from radiation. Its presence is scientifically important, showing that Mercury has a partially molten interior or other mechanisms that generate a magnetic field. For survival, however, the field is not strong enough to replace atmospheric shielding. The surface remains exposed. Mercury's gravity is about 1/3 of Earth's, similar in magnitude to Mars. This is not the main survival limit for short exposure, but it matters for long-term health and movement. Lower gravity reduces the mechanical loading on bones and muscles. Over long periods, this can contribute to weakening unless exercise and countermeasures are used. For surface work, lower gravity makes it easier to lift objects, but it also changes balance and traction. The regolith is fine and can behave like loose powder. Without air, dust can cling through electrostatic effects. A suit must be designed to resist abrasion and to keep dust from damaging seals and joints. Micrometeoroid impacts are another concern. Without an atmosphere, small particles strike the surface directly. Over long time, this produces the cratered landscape. For a human habitat, impacts pose a risk of puncture or erosion. Shielding using layered materials and regolith coverage reduces risk. In a suit, puncture risk is low at any instant but cannot be ignored over repeated outings. Pressure containment remains the most critical safety requirement. A suit failure in vacuum is fatal quickly, regardless of temperature. Survival on Mercury becomes more nuanced when location is considered. There are regions near the poles that remain in shadow, including crater floors that never receive direct sunlight. These permanently shadowed regions can be extremely cold and may preserve water ice, delivered by comets or produced by interactions with solar wind. Such regions offer potential resources and also provide stable cold, which is not comfortable but can simplify thermal management if a habitat is insulated and heated internally. In contrast, equatorial regions in full sunlight pose extreme heating challenges. The most favourable locations for long-term presence, if any, would likely be areas with moderate solar exposure or sites where habitats can be built beneath the surface to avoid direct thermal extremes. In strict survival terms, unprotected life on Mercury is not possible because of vacuum. The time a human could survive without a suit is short, limited by loss of pressure and oxygen. With a suit, survival time is limited by life support supplies and by the suit's ability to manage heat and radiation. In bright sunlight, the cooling burden is high. In shadow, the heating burden is high. A habitat can extend survival far longer by providing stable internal conditions and using local material for shielding. Such a habitat would need reliable power, likely from solar collectors positioned to avoid shadow, from nuclear sources, or from a combination. It would also require careful thermal design to deal with long days and nights. Mercury therefore represents the inner extreme of an airless world close to the Sun. It combines vacuum with intense solar heating in daylight and profound cold in darkness. It adds increased solar radiation exposure compared with more distant airless worlds. It offers no natural breathable refuge and no atmospheric pressure. Survival there, as elsewhere beyond Earth, exists only inside engineered protection. The difference is that Mercury demands that protection handle not only vacuum, but also a severe thermal environment driven by proximity to the Sun and a slow rotation that keeps regions in one lighting condition for long spans. Closer to the Sun, survival in space is shaped less by cold and more by radiation and heat management. The Sun is not only a source of light and warmth, it is a source of charged particles, magnetic disturbances, and sudden energetic events. Throughout the solar system, solar wind flows outward as a continuous stream of plasma, and from time to time the Sun releases bursts of energetic particles associated with solar flares and eruptions in the corona. These events can increase radiation levels sharply for hours or days. The closer a person is to the Sun, the stronger the incoming energy flux becomes. This changes how quickly equipment heats in sunlight, how easily it can shed that heat, and how intense particle exposure can be outside strong shielding. In open space, unprotected survival is still limited first by vacuum, because breathing and pressure control are immediate necessities everywhere. Yet once a suit or spacecraft provides pressure and air, the dominant environmental pressures shift. In the outer solar system, cold and limited sunlight drive the need for heating and long-lived power sources. In the inner solar system, sunlight is abundant, and the major challenges become overheating, ultraviolet exposure, and the ability to withstand solar particle events. A suit in near-Earth space already balances cooling and heating. Closer to the Sun, cooling becomes more difficult because the external environment is more energetic, and because the surfaces of suits and spacecraft absorb more solar radiation unless they are carefully reflective. Heat exchange in space works mainly through radiation. A system cools by emitting infrared energy from its surfaces. It warms by absorbing sunlight and by absorbing infrared radiation from nearby hot surfaces. Near the Sun, sunlight is more intense, so absorption becomes a stronger heating term. Near a hot planetary surface, such as Mercury's day side, reflected and emitted infrared radiation adds further heating. A spacecraft must therefore manage its orientation and surface properties carefully. Reflective coatings reduce absorption. Radiators must be positioned to face cold space rather than the Sun. Shade structures can block direct sunlight. These methods are used in solar probe engineering, where spacecraft operate close to the Sun with large heat shields and carefully managed thermal systems. For human survival, these thermal facts translate into strict design constraints. A spacesuit keeps a person alive partly by removing excess heat. The body produces heat continuously, and physical work increases it. A suit uses circulating cooling fluid and radiators to reject heat. When sunlight is intense and the surrounding surfaces are warm, the suit must reject heat into an environment that is already supplying heat. Cooling remains possible, but the margin becomes smaller. A failure of cooling can lead to dangerous overheating. This is not a slow discomfort. Heat stress can impair judgment, reduce performance, and threaten life if core temperature rises too far. Solar ultraviolet radiation is also more intense closer to the Sun. Earth's atmosphere blocks most ultraviolet at the surface, but in space it becomes a direct exposure. Spacesuits and spacecraft materials must resist ultraviolet degradation and must protect skin and eyes from exposure. Protective vices and shielding layers can do this, but long-term material aging becomes more severe in stronger ultraviolet environments. Polymers can become brittle, coatings can degrade, and seals can weaken over time. This affects not only comfort but reliability, which is central to survival in vacuum. Solar particle events are another major concern. During a solar flare or a coronal mass ejection, the Sun can accelerate protons and other particles to high energy. These particles can reach planets and spacecraft, increasing radiation exposure near Earth. These events can affect satellites and pose risk to astronauts. Closer to the Sun, particle flux can be higher and arrival times can be shorter. Shielding and operational planning become essential. A spacecraft can include a storm shelter, a region with extra mass around it, often using water and supplies as shielding. Astronauts can retreat there during high radiation periods. The effectiveness depends on shielding thickness and on the energy of the particles. Even with shelter, intense events can impose limits on how close and how long humans can remain in exposed regions. The Sun also shapes the magnetic environment of the solar system. The solar wind carries the Sun's magnetic field outward, creating a complex, changing interplanetary magnetic field. This affects how charged particles travel and where they concentrate. It also interacts with planetary magnetospheres, creating radiation belts and auroras. These interactions can increase local radiation in certain regions, as seen dramatically near Jupiter. In the inner solar system, Earth's magnetosphere provides substantial protection on the surface, but in space the protection is partial. For planets without strong magnetospheres, such as Mars, solar particles reach the upper atmosphere more directly. For an astronaut in transit or on an airless surface, the solar environment becomes the primary driver of short-term radiation hazards. Proximity to the Sun therefore changes the practical definition of safe travel. A mission that stays near Earth can plan around known radiation risks and use Earth as a partial shield when in certain orbits. A mission that travels inward toward Mercury must carry its own shielding and thermal protection. In that inner region, even the concept of a comfortable EVA becomes more difficult because sunlight is harsh and cooling is challenged. A habitat on Mercury would need thick shielding not only against cosmic rays and micrometeoroids, but also against solar energetic particles. It would also need thermal design to prevent overheating in sunlight and freezing in shadow. The Sun's influence becomes the background condition for every engineering choice. These solar effects also apply in smaller ways across the entire solar system. Even far from the Sun, solar storms still occur and the solar wind still moves outward, yet the intensity declines with distance. In the inner solar system, intensity is high. This is one reason why the survival spectrum cannot be described only by atmosphere and pressure. It must also include the energy environment, especially radiation and thermal flux. A person on the Moon faces vacuum and radiation, but the sunlight intensity is moderate compared with Mercury. A person near Venus faces extreme surface heat from the greenhouse atmosphere, while sunlight intensity is also high. A person near Mercury faces both vacuum and intense solar heating. Within this region of the journey, the Sun is not treated as a place to stand upon, but as the central source that changes survival conditions in every inner location. Survival time in space is not limited only by breathing and pressure once those are supplied. It is limited by how well systems manage heat and radiation over time. Heat can overwhelm cooling, radiation can accumulate. Solar storms can deliver sudden surges, materials can degrade, electronics can fail. These are not dramatic threats in appearance, they are steady constraints, and they become stronger closer to the Sun. In calm terms, the Sun's influence compresses the safety margins. It makes the inner solar system a place where protective equipment must do more work, rejecting more heat and shielding against more energetic particles. It makes time more valuable because exposure rates rise. It encourages the use of shelters, reflective surfaces, and thicker shielding. It also makes the stable shelter of Earth's atmosphere and magnetic field more clearly distinct from the environments of nearby worlds. The inner solar system is bright, but brightness is not comfort. It is energy, and energy must be managed continuously for survival to continue. Survival time across the solar system is not a single number for each planet. It is a relationship between human biology and the local physics of air, pressure, temperature, and radiation. When these conditions match the needs of the body, survival can be long and continuous. When they do not, survival becomes a countdown, extended only by technology that recreates a small patch of Earth-like conditions. This relationship remains steady from the outer darkness to the inner heat. It is not a matter of courage or will. It's a matter of pressure keeping lungs functioning, temperature staying within tolerable limits, and radiation exposure remaining low enough for tissues and systems to endure. The simplest divide is between places with usable atmosphere and places without it. Earth provides a breathable mixture at a stable pressure, along with temperature ranges that allow liquid water and normal bodily function. Everywhere else, atmosphere either does not exist or does not help. The Moon and Mercury are essentially vacuum at the surface. An unprotected survival there ends quickly because breathing stops and pressure disappears. The asteroid belt is the same, a wide region where vacuum dominates and the suit becomes the only environment. Mars has an atmosphere, but it is too thin and composed mostly of carbon dioxide, so it cannot support breathing and it cannot provide sufficient pressure. Venus has an atmosphere that is far too dense and far too hot, making it lethal by heat and pressure. Jupiter and Saturn have deep atmospheres of hydrogen and helium with no solid surface, and pressure rises continuously with depth. Uranus and Neptune are similar in the sense that they offer no solid landing surface, and they deepen into crushing pressure and increasing heat. In every case outside Earth, the body cannot simply adapt, it must be enclosed. Pressure is the first immediate limit because the body requires it for gas exchange and for fluid stability. In vacuum, breathing stops and consciousness fades quickly. In extremely low pressure, water becomes unstable and lung function cannot proceed normally. In extremely high pressure, the body and lungs are compressed beyond safe limits, and normal function fails. This is why the survival spectrum contains both airless worlds and overpressured worlds as equally lethal in different ways. The body needs not only oxygen but oxygen at the right partial pressure, within a total pressure range it can tolerate. Temperature adds the second major limit. On airless worlds like the Moon and Mercury, temperature swings are extreme because there is no atmosphere to store and distribute heat. A suit must manage intense sunlight and deep shadow. On Mars, thin air provides little buffering, so nights can be very cold. On Venus, thick air and greenhouse warming produce continuous extreme heat that cannot be escaped by shade or night. On the giant planets, upper atmospheres are cold while deeper layers become warmer and then dangerously hot as pressure rises. For survival, this means thermal control is always required outside Earth, but the direction and severity differ. Sometimes the main task is heating. Sometimes it is cooling. Often it is both, depending on location and time. Radiation becomes the third major limit over longer periods. Earth's atmosphere and magnetic field reduce radiation exposure at the surface, in orbit, on the Moon, and on Mars. Radiation exposure rises because shielding is weaker. Solar particle events can add sudden increases. Cosmic rays provide a continuous background. Near Jupiter, radiation belts can become intense enough that time near certain orbits is sharply limited without heavy shielding. In the outer solar system, cosmic rays remain present, and distance makes rescue and repair harder. Radiation is therefore both a health risk and a reliability risk for equipment. It is often not the first thing that kills in an unprotected scenario, but it becomes decisive for long-duration living. The fourth major limit is the availability of resources and the feasibility of shelter. A suit extends survival only to the limits of oxygen supply, carbon dioxide removal, water, battery power, and thermal control. A spacecraft extends survival further by carrying more supplies and better systems, but it remains finite without resupply and recycling. A habitat can extend survival for much longer if it provides stable pressure, air, water, food, and temperature. The best habitats also provide thick shielding, often by using local material. This is easier on solid bodies where soil or rock can cover a living space. It is much harder within deep gas atmospheres where there is no ground and where pressure gradients make stability difficult. This is why moons and rocky planets are more plausible for long-term shelters than the interiors of gas giants. In the outer system, the main added difficulty is power. Sunlight is weak near Uranus and Neptune and weaker still beyond them. Heating and life support systems cannot rely on large solar input alone. Long-duration survival would depend on nuclear power or other long-lived sources. In the inner system, sunlight is strong, which can support solar power, but it also increases thermal load and radiation exposure. The sun becomes both a resource and a hazard, and thermal design becomes more demanding. When these factors are placed together, a calm pattern appears. In vacuum or near vacuum, unprotected survival is short because pressure and oxygen are absent. In dense hot atmospheres like Venus, unprotected survival is essentially none because heat and pressure are overwhelming. In deep gas giants, survival is limited to the region above the crushing depths, and even there it depends on floating platforms and sustained control. In thin atmospheres like Mars, survival depends on pressurized suits and habitats, with radiation and cold as continuing constraints. On airless, rocky bodies like the Moon and Mercury, survival depends entirely on sealed systems and on handling temperature extremes and radiation. Earth stands alone as the natural baseline. It provides breathable air, stable pressure, and liquid water. It buffers temperature and reduces radiation. It also supports food webs that allow life to continue without carrying all resources in sealed tanks. This is why survival on Earth is not best described as minutes or hours. It is described as ordinary life. The other worlds can be compared only by asking how long a person remains alive when the protective boundary fails, or how long a sealed system can maintain Earth-like conditions before resources or reliability are exhausted. Within this inward journey, the idea of surviving on each planet becomes less about the planet and more about the interface between the body and the environment. A human does not survive Jupiter by standing on Jupiter. A human survives near Jupiter only within shielding and controlled orbit. A human does not survive Venus by breathing Venus. A human survives near Venus only inside strong insulation and pressure-resistant design, likely far above the surface. A human does not survive Mars by using its air. A human survives Mars by bringing air, pressure and warmth and by shielding against radiation. The planet sets the outside conditions. The habitat sets the inside. The solar system therefore presents a spectrum of environments, each governed by the same physical laws, each indifferent to biology. Survival is the act of carrying a small Earth-like pocket across these environments and keeping it stable. The farther that pocket is from Earth's natural support, the more it depends on power, shielding, and reliability. The survival clock begins when pressure and oxygen fail, and it slows only when engineering holds. In the end, the calm fact remains simple. Humans survive where water stays liquid, where air supports breathing, where pressure supports lungs, and where heat and radiation remain within tolerable limits. Earth provides these without effort. Every other planet does not. Across the solar system, survival becomes a measure of how long technology can replace what nature provides only here. The thought settles into stillness. Planets continue on their paths. Vacuum remains between them. Sunlight spreads outward and fades. The body's needs remain constant. A sealed suit and a warm shelter remain the thin boundary between life and the wider space beyond.